All right, there we are. So we are now recording and we are ready to get started on significant figures. So I'm going to switch from looking at all your beautiful boxes and we will, I will share my screen and we'll go back to the slides where we left off on Wednesday. So you should be seeing the screen filled with our chart of numbers and measurements, actually, um, that we were identifying how many significant figures were in each of those numbers. So to recap real quick, the rules are any digit that is in a measurement that is not a zero is a significant figure. Any zeros at the beginning, so on the left side of our uh, measured value, so like 0 point something, any of those zeros at the beginning, right, no matter how many there are and whether there's a decimal or not, it doesn't matter. If they're at the beginning on the left side, they are not significant. They are just really there sort of showing you the size of that number and that the size is very small. In fact, if you wrote those numbers in scientific notation, all of those zeros at the beginning would vanish, right? So they're really truly there just to show you the size. Any zeros that are in the middle, right? So look, we have a couple of examples on this chart. Any zeros in the middle, we call them trapped zeros. Those are all significant. Those are all things that were measured. They just happen to, right, be measured at a value of 0. And then our zeros at the end, which are always troublesome. The zeros at the end, if there's no decimal place, they are not significant. Right? Again, just like the ones at the beginning, they're just there to show that it's a really big number, right? That the decimal point is, even though it's invisible, is way far over on the right. If there is a decimal point, then all the zeros at the end, again, whether they're before the decimal or after, become significant. So it gets challenging when we're trying to show that some of the zeros at the end are significant and some aren't, and that's when scientific notation really helps us out. So we have that example at the bottom there, the very last one on the rightmost column. We can underline the zero that is significant and leave alone the zero that is not significant in that number. Or we could put it in scientific notation, and then it's much clearer if we wrote that as 5.40 times 10 to the third. That would clearly show that one of those zeros is significant and one of them is not. It's not included in there. So scientific notation is helpful. All of the numbers in the coefficient part are significant. The power of 10, again, is just telling you the placement of the decimal point. So there's no significant figures in that power of 10 part of our scientific notation. All right. I guess it wasn't as brief a review as I thought. That's pretty long-winded. But thorough. So did that bring to mind any questions or any examples or maybe something you started practicing with that you want to ask about? Okay. All right. So seeing none. Again, if it comes to you later, please jump right in. So what we're going to see today, right away, is how our topics really all build on each other. We've looked at this skill of counting significant figures. We're going to look at the skill of rounding numbers, right, to the appropriate number or place of significant figures. And then we're going to look at the rules for significant figures, and then we're going to put it all together. So we've got sort of 3 very distinct individual skills, and then we're going to try and very quickly put them all together and solve a problem. And that is really a lot of what we're going to be doing this semester. We're going to be learning lots of little skills, any one of which may not trip you up, but it's always more challenging when we try and hook them all together. It's going to amplify any weaknesses we have in any of those sort of foundational skills. So this week where we're laying a lot of foundation, It is super important that we really work on not just doing okay on understanding things, but really, really being, I don't want to say flawless, but working towards that 100% correctness on some of these skills. That's just going to make building on them a little better. We're gonna keep not just build on them and say too bad if you didn't get it, but we're going to keep using them. So we're going to get to practice the skill of how many significant figures are in a number. That's going to be a question we ask ourselves all semester long, as we're putting that as a part of a bigger problem. So realize everything we're doing now, we're going to see again, not just in the short term, but in the long term. So any effort, any time that you invest in yourself and your understanding now is definitely going to pay off down the line, right? We don't want to still be tripping over significant figures in week 12, right? We don't want to still have that problem. So again, any sort of extra effort you can give to really mastering these ideas now is going to pay off later. Alrighty. So first skill was counting significant figures, and we've got that down. Okay. Our second skill is going to be rounding numbers. So there's a lot of different rounding rules out there. But we're gonna make it real simple, right? If the number after you're rounding is a 5 or bigger, we're gonna round up. If the number after the number that you're rounding to is less than 5, so 0, 1, 2, 3, or 4, we're going to just leave all of those extra digits away, and we're not going to change our number of interest. Again, and if our digit is 5, 6, 7, 8, 9, we are going to round that digit up. Okay, so let's look at a couple of examples for that. So we'll come back to that chart in a minute. We want to put our eyes down in the bottom right corner. And we've got two different ways we will be rounding. We can either round to a number of significant figures, right, where we want to keep a certain number of significant figures in our answer, or we can round to a position, sort of what place do we want to keep things. So we're going to have to remember when we learned, I don't know, back in, I don't know, third grade, fifth grade, whatever that was, about the different positions, the ones place, the tens place, the 100ths place. So we'll use some of that math language again today. But we can round it to two different ways. So let's look at the top situation where we're rounding to 3 significant figures. So that SF is my lazy way of writing significant figures. We will see that all semester. So if you see on your paper SF error, that means there was an error in your significant figures. All right, so SF for significant figures. So if we look at that first number, 78.035, and let's suppose we wanted to round that to 3 significant figures. So we would count, right? We would start on the left and count all the significant figures and stop when we get to 3, right? So we would do the 7, the 8, and then the 0. That's 3 significant figures. And then we're going to look what comes immediately after the 0. We don't care what comes way after it. We're not looking way down the line, right? We're going to look at what comes immediately after it. And that right after that 0 is a 3. So do we need to round that 0 up to make it a 1, or are we just going to leave it as a 0?
We're leaving it.
We're just going to leave it, right? Because that 3 is less than 5. So we're going to end up with 78.0. That number, that final result that we're reporting, has 3 significant figures. Okay, well, let's see how it's different for the number right underneath it. So 78.075. Again, we're going to round it to 3 significant figures. Right, so we're going to start and we're going to count 3 significant figures. Right, and then we're going to look at what comes right next. So we'll start with the 7, and then the 8, and then the 0. That's 3 significant figures. We're going to look at what comes right after that 0. Okay, it's a 7. So do we round that 0 up, or do we leave it be?
We round it up.
We are going to round it up. Yes, we are, right? Because 7 is bigger than 5. So that becomes a 78.1 there. Okay. All right. So that's when we have to round to a number of significant figures, which is are going to be our rule when we multiply. But our rule for adding is different, and sometimes we'll have to round to a certain position, a certain power of 10. So that's going to be different. We aren't going to care about how many significant figures there are at all. We may end up with more or less than we had before. We're not going to fret about it. Um, if we had to round to the ones place, suppose that was what our rules had told us to do. So we need to know where the ones place is, right? We have to be able to find that, and then we're going to look at what comes right after that and decide if we need to round up or not. So the ones place in this first number of 78.03, the ones place is the 8. The 8 is in the ones place. So we're going to look at what comes right after it. Right? That's a 0. So are we going to round that 8 up, or are we going to just let everything go? Yeah, good. Yep. We are in fact going to let it go, right? Because 0 definitely is less than 5. So we're going to end up with just 78. So you can see our number stops. Our last significant digit is in the ones place, right? We didn't worry about how many significant figures there were total, just that we knew we had to stop at that position. All right. In the bottom number, it's a little bit different. Again, let's say we still are rounding to the ones place. So again, we're going to look at that 8, and we're going to look at what comes right after that 8, and that's a 9. So what are we going to do? Are we going to round our 8 up 1, or are we going to let it go? Awesome. Good. Yeah, we are going to round it up because 9 is definitely bigger than 5. So it becomes a 79. Okay. So the chart at the top is your reminder that your dear calculator, right, as smart as we think it is, because it can do all these calculations and all this computations, um, really doesn't keep track of this. It has no sense of significant figures, right? That is the math way of looking at numbers, right? They're not looking at what it represents or how well we know anything or what it means in the real world. Your calculator gives none of that. So on the left side of that chart is the situation that we have typically, which is that your calculator gives you all these digits, and we have to round and lose some of them because there's too many. There's just too many digits properly to account for our number of significant figures. That's typical, and that's what we have been doing mostly. On the far right of that chart is when your calculator has too many digits. Sometimes your calculator gives you an answer of 6, and maybe you're supposed to have 3 decimal places in your answer. So what are we going to do? Right? Our calculator is showing us a 6, but we know we need 3 decimal places in our answer for proper significant figures. So we have to add some significant figures, but we don't want to add random numbers, right? We don't want to change the results, right? Or change the value or the size of our result. So we're going to add significant zeros. That's not going to change the value or the size or any of that. So our 6 in that case would become 6.000, right? Again, mathematically, that's the same as 6, but significant figure wise, it meets our requirement of having 3 decimal places for significant figures. And in the middle is a rare situation. Occasionally our calculator stumbles into the right answer. But it's not because it thought about it. It's just an accident. But every now and again, our calculator will have the right number of significant figures. But again, it's your job to know that. It's your job to check and see which of those 3 situations you have, and either round to get rid of digits, add zeros to get enough significant figures, or recognize that the calculator just accidentally has the right number of significant figures. So this rounding skill, again, it's often just kind of glossed over in a lot of our textbooks. I think we have a little section of it in ours. And if you started doing the practice portfolio or looked at some of those practice problems down there in chapter 1, um, it's actually going to be doing exactly what we're doing right now. Is it's going to have you practice counting significant figures, then it's going to have you practice rounding them, right? And then it's going to move into what we're going to do next, which is let's look at the different rules for this kind of math and that kind of math, and then we're going to put it all together. So the portfolio, as you're doing it, is actually building those skills for you, right? So I'm going to encourage you to check your work after each little section or type of problem so that you know you've gotten that skill well understood before you move to the next one and try and build on it. You want to make sure you're building on a strong foundation. Okay. All right, questions on rounding? So I will assure you that this will be a part of every single calculation we do from this point forward, right? Anything we do numerically, it should have the right number of significant figures in it. So we need to be able to count how many there are. We need to be able to round things properly. And when we do calculations, we're going to have to be able to know, well, which rules, what rule are we applying? Are we applying a rule where we need a certain number of significant figures, or are we applying a rule where we need to know a position? All right. So here are the two rules. Now, I will tell you, there are not two rules because we hate students and we're trying to make your lives miserable. There are two rules because the number of significant figures, remember, all has to do with how well do we know that measurement? And then how well do we know the calculations that come from those measurements? Right? That's important information to have so we know, right, how much faith to put into our results there. We don't want to overstate things and we don't want to understate things. So the way that that uncertainty, right, in every measurement sort of propagates through a math problem is different when the math that we're doing is addition and subtraction versus multiplying or dividing. You can kind of imagine if you're multiplying or dividing, any uncertainty is going to get very big very fast. Versus in addition, where the uncertainties in our measurements are just going to kind of add up over time and over calculation. So that's why there's two different rules. Okay. So let's look at the multiplying and dividing rules on the left, at the upper left there. So when we are multiplying or dividing or both, right, those are all kind of the same thing. So any of those problems, kind of like the ones we've practiced with our calculator, there was a lot of multiplying and dividing. We're going to see a lot of that in our first week or so of the kind of calculations and relationships we're working with. So we'll get real good at this rule. That rule is that the result of all of our multiplying and dividing is going to be limited by the number of significant figures in whatever measurement has the smallest number, right? So whichever measurement was done the least well, right? If you think about it that way, whoever is sort of the weakest link in that whole chain of multiplying and dividing is going to limit how well we can know our final results. Right? So if one of the measurements was done not very well, right, with a lot of uncertainty, very few significant figures, and everybody else did their measurements to lots of significant figures and lots of certainty, very small uncertainty, then when we put them all together, we still can't know the total or the final or the eventual results any better than our little friend who did things with a lot of uncertainty. So we are, in the case of multiplying and dividing, we're going to look at what are the number of significant figures in every number that we used in that multiplication or division process, right? We're going to figure out which one has the smallest number, and then we're going to look at our final answer that our calculator gives us from all that multiplying and dividing. We're going to look at that final answer, and then we're going to round it to however many significant figures we have for that multiplying and dividing. So for example, if we had this number 0.50 in our series of multiplying and dividing, and everybody else had more significant figures than 2, our final result would only have 2 significant figures. Okay? And that's different from what's going on with adding and subtracting. So if we rotate our eyes over to the right side now, at the sort of towards the bottom there, the rule is a little bit different. The rule is that when we're adding or subtracting or both, it doesn't matter, kind of the same thing. Our final result of that calculation is going to be limited by the position, not the number, the position of the last significant figure in all the numbers that we added up and subtracted. So we need to be able to figure out sort of the place, right? Is it in the ones place? Is it in the hundreds place? Is it in the thousandths place? So our example there is 13.0056. That one has its last significant figure, right? So if you go through the number and you just read and kind of see where the last significant figure is, and that number it is 6, which is in the fourth decimal place, or the 10,000ths place, the 10 to the minus 4 position, which is a pretty small uncertainty. It's a very small uncertainty. But if all of our other measurements that were being added together all had 5 or 6 or 7 decimal places, then this little friend here, 13.0056, would have its last significant figure in the largest position, and it would limit, and we couldn't know our answer any better than that. So what we're going to do is we're going to look at these two rules. We're going to go through several examples in very slow, gory detail, because this is probably not something that you walk around thinking about every day. I would be surprised if anybody really was thinking about this when they did their calculations, right? If you did any calculations in your everyday life, you probably just do the math and you kind of give your result or think about your result to some reasonable number of significant figures or decimal places, and you didn't really think about, well, why would I round that off, or why would I not? Eventually, we're gonna be able to do this sort of almost like breathing, but right now, it's gonna feel weird. It's gonna take a lot of brain cell effort and activities. So be kind to yourself and go slow. We'll kind of break it down and think about what questions do we need to ask ourselves. And again, eventually you'll be able to ask yourself those questions sort of automatically and almost without verbalizing it. So you will get faster at this, and it will be more natural. But today it might feel sort of odd and unusual. So I just want you to have that expectation. Okay. You know what, I didn't say it was gonna be hard. It's gonna feel weird because this is not something we think about, right? In a math class, if you were asked what is 4.76 times 3.0, you would just put it in your calculator and you'd give some answer, right? Maybe all the digits, maybe some of the digits, whatever. Again, in chemistry, if these are coming from measurements, they have meanings and they have limits. So we have to ask ourselves, what are these questions when we're going to report our answers? So if we're multiplying and dividing, we know that our answer is going to be limited by the number of significant figures in our measurements that we're using. So the first question to ask ourselves is, well, then, how many significant figures are in these numbers that I'm multiplying together? All right, so let's think about it. How many significant figures are in 4.76? Awesome, good. It's always easier when there's no zeros. Yes, there are 3 significant figures here. How many significant figures are in 3.0? All right, great. Yep, only 2. Yep, that 0 at the end is significant because there is a decimal point. All right, so we've identified how many significant figures are in each. Again, at some point, you're gonna be able to do this in your head. For right now, you might want to jot down underneath or on top of the numbers that are in your calculations how many significant figures there are. That might help you to sort of go through the process of, well, what all do I need to think about? All right. And what we need to think about is, well, which of those is smaller? Which is smaller, 3 or 2? Okay. Not a trick question. It sounds like it is, but it really isn't. 2 is the smallest number of significant figures, right? That means that when we're all done and we're ready to report our answer, it should only have 2 significant figures, right? Let's put those numbers in our calculator and see what we get.
So we should always go for the smallest amount of significant figures,
When we're
unless told,
multiplying and dividing, yes, it's the
unless told
smallest number.
otherwise, right?
Mhm.
Okay.
Right. So you see, we can't even apply this rule if we don't know how to count significant figures, right? So that very first skill that we worked on Wednesday, right, is coming, right? It's coming back to haunt us already, right? So we have to be good at that skill. And then we have to know which is bigger, 3 or 2. Okay. So 2 significant figures. What does our calculator give us? Gives us 14.28, right? And in a math class, you might have just written that down and carried on. But in a chemistry class, we need to report that correctly because that number came from some measurements of 4.76 and 3.0, whatever those were. So we know our answer is limited, right? We can't just write as many decimal places or significant figures as we want, right? Our answer only has 2 significant figures. All right, so can we round 14.28 to 2 significant figures? This is the skill we just worked on, right? So we're going to start at the 1, right, and count over 2, right? So we'll keep the 1 and the 4. Yep, you guys are way ahead of me. Yep. So what comes after the 4 is a 2, right? So we're just going to let that go, right? And our answer that we would report is 14. It's sort of in bold there, but what you might want to do is, circle it so you know that you've made a decision, right? Again, at some point, you're just going to have the math problem and you're actually going to just, right, put the numbers in your calculator and you're just going to write it down as 14, right? You're going to do all of this thinking that took us 3 minutes to get through sort of almost instantaneously in your head. You're not going to need to write down all these steps for the rest of our semester. So, but for right now, you might want to, right? Just till you get kind of the hang of it. And then you'll be able to just start reporting numbers correctly without, again, kind of physically writing down all these in between steps, right? So circle it or box it or something that lets you know, hey, I've made a decision. This is how I'm reporting that answer. Okay. Let's try another one with dividing this time, right? It's the same rule though. Multiplying or dividing, it's the same rule. What's important is the number of significant figures. So step 1, how many significant figures are in the numbers that you're using in this calculation? All right, so how many significant figures are in 8? All right, well, that's so sad, isn't it? Just 1. Yes. So this measurement wasn't done very well, right? It only has 1 significant figure. This person did not work real hard. We're going to divide it by 35.76208. How many significant figures are in that great big number? Wow, 7. Holy moly. Yeah, that is a lot. Somebody put in a lot of effort, right? And measured that particular value really, really, really well. And now we've put their 2 works together, right? Something with 1 significant figure and something with 7 significant figures. All right, what's smaller, 1 or 7? Just 1, right? So when we do this math, we are going to be limited to only 1 significant figure, right? We cannot do any better than the worst measurement that we've put together here, right? So that's, right? It's kind of like every group project you've probably ever worked in, right? Somebody does all the work and somebody does not so much work, and your overall grade is sort of tanked because of it. It works kind of that way with significant figures. Okay, so what does our calculator give us? What is the result from our calculator? It gives us a whole bunch of digits, doesn't it? Right? Now, even in math class, you probably wouldn't have written all of those down, right? You would have rounded that off to some reasonable number of decimal places. But we know that we are only going to keep one significant figure. All right, so we need to start counting significant figures. Is that 0 at the beginning significant? No, it's not. Remember the zeros at the front end? Never significant. So that's just they're holding or showing us that there's a decimal point there. So the first significant digit is this first 2. And that's the only one we get to keep, right? So we're going to look at what comes after that first 2, which is another 2. And then we're going to decide, do I need to make my first 2 a 3 or do I just leave it as a 2? And the answer is, of course, we're going to leave it as a 2. So our answer would be 0.2. That only has one significant figure. So again, that 0 at the beginning is not a significant digit. It's just there really sort of pointing out that there's a decimal point there. So you don't miss it. That's really what it's there for. So you don't miss it. Okay. All right. So those are our 2 examples with multiplying and dividing. All right. Do we have any questions from those 2 examples? All right. Well then, no questions on that one. Let's practice a little bit with our other rule, which is we will see less commonly sort of in our class part, but we will see it quite often in our lab. We're going to be doing a lot of sort of difference between 2 measurements in our lab. I won't say next week, but the week after that, we'll be doing quite a bit of that. So we will see that adding and subtracting rule more often in lab, which means that we're going to forget about it because we're not going to do it as often. But we want to practice it now so that when it does come up again, you can go, oh, yeah, I do remember that it's a different rule for adding and subtracting. All right. And the adding and subtracting rule is we are going to pay attention to where or the position of the last significant figure in each of the numbers that we add or subtract. So the way I've put that question there is what is the power of 10? What is the place, right, of the last significant figure? That's our SF there. In each of the numbers that we're adding together. So we've got 3 things that we're adding together here. So if we look at our first number, 999.01, what digit is the last significant figure? Oh, good. No. It's the 1, and it's in the hundredths place or the 10 to the minus 2 position. Okay, it's in the second decimal place. Right? In our middle number, 0.7, where's the last significant figure here? Yep, that's in the tenths place or the 10 to the minus 1 position, the first decimal place. And our last one also is in the second decimal place or the hundredths place or the 10 to the minus 2 place. Right, so I'm going to write those down there. So 10 to the minus 2, hundredths place, 10 to the minus 1, the tenths place, and 10 to the minus 2, also the hundredths place. Okay. So again, we're going to be limited by the measurement that was made least well, right? So the one with the biggest power of 10. So we need to look at those powers of 10 and be able to recognize, well, which of those is bigger? 10 to the minus 2 or 10 to the minus 1? So which is bigger? Yes. It is 10 to the minus 1. That's again, remember the bigger the negative exponent, the smaller the value. So yeah, so the biggest power of 10 is 10 to the minus 1. So that means, again, that our answer is limited to that. That is our limit. That's the best we can do when we combine these values. We can't know things better than the worst measurement. So when we get our result from our calculator, we're going to have to do some rounding to make sure that we end in that 10 to the minus 1 place, that first decimal place. So put that all in our calculators, right? And we'll get a value from our calculator. And it should look like, if I use my buttons correctly, 1000.08. Yes. And again, right, that's what our calculator says, right? That's not necessarily what the result is, right? It's what our calculator said. That's it. You've got to now engage your brain, right? And round that to the 10 to the minus 1 place, the first decimal place, which is a 0, right? And we look at what comes after it, right? And what comes after it is an 8, right? So we're going to round that 0 up. So yes, I think a few folks have put that in the chat box, right? 1000.1. Okay. If we had 10 things we were adding together, we would have to do this for all 10 values that we were adding together, figure out where the last significant figure was, and then select the largest out of all of those choices, right? So there's no real limit to how many things we can add together and use this rule for. Okay. Questions on this one? So again, it's a lot of little skills that we're putting together, and it's a lot of little skills you, again, probably they're not sort of natural for us. They're not things that we've done before. So again, it's going to feel probably a little awkward or a little weird, sort of artificial. But again, remember what we're doing is we're making sense out of measurements. All right. And unfortunately, until we're really in the lab and taking measurements, it's a little hard to visualize or really appreciate as much. So our first activities that we're going to do in lab next week, and our first actual real lab, the following week are going to be all about taking those measurements. So we're going to get a much better feel for that coming along. So we're going to kind of get the book learning now, and then we're gonna go and see these significant figures acted out when we go in and take some real measurements finally. All right, we've got one more of these. It's a subtraction. All right, so same questions we're asking ourselves. Where is the last significant figure? For adding and subtracting, it's a where question, not a how many. So where, or what is the power of 10 in the last significant figure? So for our first number, where is our last significant figure? What position or what place is it in? Okay, good. The thousandths, the 10 to the minus 3 place, the third decimal place. Those all mean the same thing, right? How about for our second number there? 2.5709. Where, the same question, where is the last significant figure? What power of 10? Right? The 10 thousandths or the 10 to the minus 4 position. Yes. All right. So however you want to write it out or note, I hesitate to use how many decimal places because our last significant figure is not always somewhere on the decimal side of things. It might be in the ones place or the tens place or the thousands place. It isn't always in a decimal place. So that's why I always start us out by thinking about the position of it. Where is it? We're going to do lots of things with lots of decimal places in them. That'll be common. But realize at some point we might be adding very big numbers where the last significant figure is maybe in the tens place on the other side of the decimal point. So that's going to make things a little bit different. So if we can start our understanding of this significant figure rule thinking about position, when we have significant figures on the big side of the decimal point, it won't throw us for a loop then. All right, so what is the biggest power of 10 out of these? 10 to the minus 3 or 10 to the minus 4? Awesome. Yeah. Yep, it's the same reason, right? The bigger the negative exponent, the smaller the value. So 10 to the minus 3 is going to be our bigger value there. All right. And again, what that means is that after we put all those numbers in our calculator, right, hit that equals button, whatever our calculator says, right, we can only report that out to the 10 to the minus 3 place, right? Anything after that is not significant. We're kind of just making up those digits, right? Because they're really not accounted for in the uncertainty of those measurements. Right? So here's what we get from our calculator, 0.6621. We're going to round it to the third decimal place. So that's where the 2 is sitting. And when we look at what comes after that 2, it's a 1. So we're just going to let it go. And we're going to report that out as 0.662. All right. So again, we let our calculator do the computations, right? We weren't doing long division or subtraction and, borrowing and carrying the 1 or any of that. But we didn't just take our calculator's results blindly. We applied some meaning to it by using our significant figure rules. Okay. So before we go anywhere else, let's see if that brought up any questions for adding and subtracting significant figures, or if you've got a question about multiplying that you just thought of. Okay. Awesome. All righty. So I have a question for you then. What if our calculation has both kinds of math in it? What if we're dividing and subtracting in the same problem? Holy cow, what are we going to do? Which rule, right? Which rule is more important? What are we going to do? So hopefully we will not be like SpongeBob and we will not panic and go, oh dear, what do we need to do now? But what we're going to do, yep, we're gonna use the order of operations. We're going to do the math in the order that the problem, right, is set up to do it. So we're going to pay attention to parentheses, and things raised to power, all of those things. We're going to pay attention to those orders of operations. So you can see why we did that on Monday, right? We had to do that first before we could even talk about that today. Um, and then we're going to apply the rules as we go, depending on whatever math we're doing at each step. But we're not going to round things off, right? So we're not going to sort of complete the process. We're going to track the process. We're going to keep track of where that last significant figure should be, as we move forward from one step to the next. But we're not gonna hit that clear button on our calculator. We're just going to leave all the digits in there until we get to the very end. That avoids the problem of sort of rounding and then rounding and then rounding until your answer really doesn't have any meaning anymore. So we're going to see that a lot in our lab, right? We're going to have our data, something we measured, and then we're going to calculate something from it. And then we're going to take that value and calculate something else and something else until we finally get to whatever our ultimate goal was. So our best practice is to pay attention and be mindful of where that last significant figure is and report things correctly for the in-between steps. But we're not going to hit the clear button on our calculator. Okay. Sometimes it doesn't even make a difference. Sometimes it does. So we're going to do a couple of examples where we see what we mean by tracking things without clearing out our calculators, right? So I've got a couple of examples for us to practice with that. They have some tricky rounding problems in them too. So we'll get to kind of go back and sort of revisit that skill again, as we are going forward as well. All right. All right, enough SpongeBob. He is making me nervous. All right. So this is what we will call our advanced significant figure calculations, where we've got more than one thing going on at a time. Pretty common, right? Nature gives us lots of different ways things are combined. We have to apply those rules in the order in which they happen, right? So this problem has some addition that's happening in parentheses. So we are going to apply the rule for addition first, right? So we're going to do that addition first and look at what the result of that calculation is, right? So if we put those numbers in the parentheses in our calculator, we got 1069.01. Again, that is what our calculator says. but we have to be smarter than our calculators, and I'm sure we are. We're going to look at those numbers that we added together and think about, well, where should I have stopped? I should not have written down 1069.01. Right? I'm going to be limited by the position of this last significant figure that is in the largest position. Okay, so let's look at this. Our 99.01 has its last significant figure in the 10 to the minus 2 place. Where's your last significant figure in this number, in 70 with a decimal point? Where it's in the ones place. Good, right? That little dot there after our 0 is saying that all the zeros at the end are significant. So that 0 is significant and it is in the ones place. So we have a last significant figure in the ones place and a last significant figure in the 10 to the minus 2 place. So which is bigger, 1 or 10 to the minus 2? Yeah, it's the 1. All right, what that means is that this answer that we wrote down, this 1069.01, by all rights, should have stopped at the ones place. So instead of clearing our calculator out and writing 1069, we're just going to track the process here. So we're just going to underline where we should have stopped, right? And that underline is telling you where the last significant figure is. All right. Then with that sort of in mind, now we can go ahead and do the next sort of kind of math, which is going to be a multiplying here. We're going to be multiplying 0.15 by the result of that addition. And the rule for adding is, or not the rule for adding is, right? The rule for multiplying, since we're doing multiplying now, depends on the number of significant figures. Pauline, go ahead.
So when we're multiplying by the result from the addition, are we multiplying by the calculator result or by the significant figure result?
We're going to be multiplying by the calculator result, right? So we're going to save all of our rounding for the very, very end.
Thank you.
Yep. That's what we mean by tracking it instead of rounding it off after each step. Yeah. So your calculator's already sitting there showing you 1069.01. All you have to do is just not hit the clear button. That's all. So before you write those, don't get carried away with your clear button on your calculators, because you may be doing more with that value. You may be carrying on with it and doing something else with it. So again, if we were going to report our result from that addition, we would report it correctly as 1069. But in this case, since we're going to go do something else with it, we're going to, again, sort of not clear our calculator, but just go ahead and leave it there and then do this multiplication now. Right? And when we do that multiplication without having cleared our calculators, we get 160.3515. And now we've got to think, right? How many significant figures should be in that answer? Well, the answer to that is it depends on what we did to get there. So we have to go back to 0.15. And how many significant figures are in 0.15? Yeah, awesome. Good. Yeah, there are 2. Again, that 0 at the beginning doesn't count. How many significant figures are in the number in parentheses here? So it looks like 6, but remember, all of those digits are not significant because we should have stopped where that 9 was, right? So just because you wrote down a digit doesn't mean it's significant. Okay? That's why we underline that 9. That says that's where the last significant figure should be. If we had actually rounded it properly, there'd really only be 4 here. So we're multiplying something with 2 significant figures by something with 4 significant figures. So how many should be in our answer? How many significant figures should be in our answer? Right, it's the smaller number. So 2. All right. Now that we've answered that problem, we need to then go the last step, which is, okay, well, now let's take our number, 160.3515, and round it to 2 significant figures. Right? So you're going to keep the 1, you're going to keep the 6, and you're going to look at what comes after the 6 and decide what to do with that. All right, so how should we report that final answer? Okay, so you can, again, we've had some questions in the chat box. You can put this in scientific notation if it makes you feel better. You can leave it as just in a decimal form. Nowhere in this problem did it say to do it one way or another. So whatever is easier, right? Sometimes to show significant figures, it's easier to be in scientific notation. So yes, you are free to do that if you want. What you're not free to do, what you can't do, is change the size, right? Or the sort of the numerical roughly value of this just because we've rounded, right? So 160 is a good answer, right? You'll note there's no decimal point after that 0 in 160, right? If we put a decimal point after that 0 in 160, then we would have 3 significant figures, and that's not what we're supposed to have. So yeah, so 1.6 times 10 to the positive 2 is also an acceptable answer. Completely up to you. Which again is another reason we worked on scientific notation earlier, right? So sometimes the answers, when you're, say, working on your portfolio, sometimes the answers in the back of the book will be in scientific notation, and maybe you didn't use scientific notation. Or sometimes it's in decimal form when you use scientific notation. You need to be able to recognize when you might have the right answer, right? Because you agree with the answer key, but you've just written that in different forms. So kind of keep your eye out for that. If you're checking your work for your portfolio and you think, oh my gosh, I got this wrong. I wrote 160, but the answer key says 1.6 times 10 to the 2. Right? Realize that you are actually agreeing with each other. And you just need to kind of be kind of mindful, just kind of aware that it's up to you how you present that answer. Unless you're specifically asked to put it in one form or another, that is a decision you get to make. So you have powers already. All right, good. Okay. Other questions on this one? All right, so we have a question in the chat box, which is a good one. So I'm going to read it out loud. It says, so it looks like the last thing we did kind of sort of controlled how many significant figures that we should have. And the answer is that is not always the case. If for some reason, say when we added those numbers together, we ended up rounding to a certain position and we ended up with only one significant figure, then that would have limited us. So yeah, so you're not going to be able to look at that problem and go, well, I'm going to look at the last math and just round it that way. Sometimes that works, but that's not a guarantee. So you definitely want to track that math all the way through. Again, with adding and subtracting, it's the trickiest because depending on the size of those numbers, you might end up with more or less significant figures than either of your numbers that you started with. And then when you go ahead to multiply it by something else, it could in fact be the thing that limits you. So yeah, so unfortunately, there's no sort of shortcut there where you can look at the last thing you do and say, well, that's in charge. It's the cumulative effect of all of them. All right, let's do one more. Same numbers, but we're going to do the math in a different order. All right, so let's just do the math a little bit differently. All right, so this time we're going to multiply first, right? That's our order of operations. We're going to do the multiplication first, and then the addition. That's the last rule. So we're going to do the same strategy we used last time. We're going to do the math we need to do first and apply that significant figure rule. And then we'll do the other math that we're going to do and apply that significant figure rule. All right. So I think this might give you a good sense of how it's not always the first thing or the last thing that controls what's going on in that problem. All right. So if we put that, just the multiplication part in our calculator, we get 149.8515 And then we have to think about that. So where should we have stopped? We probably shouldn't have written down all of those digits. How many significant figures should be in that answer from just the multiplication part? Okay. So how many significant figures are in 0.15? Just two. How many significant figures are in 99.01? A lot more. Yeah, 5 over here. A lot more. All right. That means that our answer can only have 2 significant figures. So can we underline where the second significant figure would be in that result? Right? Again, remember, just because we wrote down 149.8515, that does not mean that there are 7 significant figures. There really are only 2. The other digits we wrote down are not significant. We just made them up. Based on those measurements that they came from, we really can't report that level of detail, right? So we really should have stopped after the 4, right? That should have been our last significant figure. And if we were reporting this correctly, we would round it up, right? And we would report it correctly. But for right now, because we're kind of in the middle of a problem, we're just going to leave it there with all of its stuff after it and just underline where we should have stopped. Right? Now we're going to add. Now for adding, we have to think about the position, the where is the significant figure. All right, so let's look at this number with all of its nonsense here that we just underlined the 4 in. What position is the last significant figure in? Where is the 4? It's a little trickier when it's on that side of the decimal point. Yeah, it's in the tens place. So the 10 to the positive 1 position. And how about our 70 with a decimal point? Where is that last significant figure? Yeah, that one's back in the ones place where it was before. All right, so when we add them together, we're going to be limited by the biggest power of 10, right? Which is going to be the tens position, right? So when we add these together, we need to stop in the tens position. Okay? And if you look back at the numbers we started with, that was not going to be apparent from any of the things that we had going on there necessarily. All right, so this is what our calculator gives us. Right? 219.8515. But we need to round it to a position, to the tens place. Right? So we're going to keep the 2 and the 1. 2 and the 1, that's in the tens place. And what are we going to do? What are we going to do to that 1? Are we going to leave it be or make it a 2? Yeah, we're going to round that up because what comes right after that 1 is a 9. Right? So we're going to round that 1 and turn it into a 2. So how are we going to report this answer? Yeah. See, it's always trickier when you're rounding on that side of the decimal point. Yeah. So 22, right? That's if you just keep the 2 and the 2 and you're like, okay, it's 22. But think about it. That's a real different value, a real different size than this 219 something that it was, right? So we want to keep the same size. So there's a 0 that we have to add on there. That's not significant, right? So there's no decimal point. So 220 would be how we report this one. So kind of like the last one when we rounded to 2 significant figures, we ended up with 160. This one we have to round to 220, or you could put it in scientific notation. 2.2 times 10 to the 2. So yeah, so kind of always watch out. Anytime you're rounding on the big side, so on the left side of the decimal point, kind of be careful that when you write your result down, you haven't made the number smaller than it should be. That's one to watch out for. We'll see that again in a couple of our labs when we're dealing with large values instead of things that are all in the decimal point. questions on that? Okay, so I've got one more example for us. Again, it's another combination one. All right. So for this one, we have all these different temperature scales. And right, a lot of us are going into nursing and other health professions. Right. So we are one of the few places that still uses Fahrenheit as a nonsensical unit there. But there are relationships for all of these temperatures, ways to convert from one to another. So we can communicate with other medical professionals or scientists in other parts of the world that are not using this silly Fahrenheit unit. We have all these equations that relate these different scales there. Um, one thing to point out in these conversions, all of the numbers in these relationships, in these equations, are exact numbers, right? These are definitions of what these temperature scales are. They're all relative to each other. So even though some of those numbers are whole numbers and some of them have decimals in them, they're all exact numbers. So to throw our brains back to where we were on Wednesday, that means that these numbers have no uncertainty in them. In fact, if we were to write them out to show how perfectly perfect they are, we would have to write out something like 32.0000000 on into infinity. And we're just not going to do that. But we are going to just have in our heads, these are exact numbers. That means that they're not going to limit our calculations in any way. So when we use them, right, when we're adding them or multiplying them by values that we did measure, realize that an infinite number of significant figures or a position of the last significant figure in the infinitieth position is always going to be the one that does not limit our calculation, right? So that 32 or the 9 or the 5 or even the 273.15, that's not going to limit our results. We're going to be limited by whatever temperature we've measured in Fahrenheit or Celsius units. All right, so let's take a real example with these equations. And suppose you've got a fever of 102. I hope you don't, because that's not good. Let's try and convert that. Suppose we're trying to talk to a specialist over there in Europe somewhere, and they do not understand 102 Fahrenheit. We need to convert that so that it makes sense to them, and they can get a sense of is that good, bad, or indifferent. So we need to use those equations that we have, right? So I will give those to you, except for the last one, the Celsius to Kelvin one. We will use it a million times over the course of the semester. So that little bit of memorization should be pretty easy. But I'll give you all the Fahrenheit and Celsius ones. So let's pick one that makes our lives easy. Let's pick this one to figure out our degrees Celsius relationship. We could use the other one that starts with degrees Fahrenheit, but then we'd have to do algebra. I don't feel like doing algebra today, so let's not do that. Let's pick this one. And what we'll do is, now that we've identified the relationship we're using, now we can go ahead and put our values in there. So our Fahrenheit temperature is 102. Remember, somebody measured that temperature, right? Somebody put a thermometer in you or on your head or something, right, to measure that temperature. So that is limited, right? It depends on what kind of measuring device we used. It only measured to the nearest 1 degree. Yeah. So yeah, so the textbook might have a slightly different version of this, and that's fine. It's going to be the same. It's just a little algebraically written, a little different. That's all. All right. So either one you use, you'll get the same answer, whether you use the one in the textbook or this version of it. They all mean the same thing. You just have to make sure that you are using the one that's going from Celsius to Fahrenheit or Fahrenheit to Celsius so that you get the right value in the right place. Okay, so if we put in again, you can see what's happening. We've got 2 different kinds of math going on in here. So we're going to do them in the order that they present themselves. So we have to do those parenthesis ones first. All right, and when we do that, right, when we do the result of 102 minus 32, right, we get 70, right? But I can't just write 70. I have to write 70 with a decimal point, right? Because that 102, its last significant figure, is in the ones place, right? My 32, remember, is an exact number, so it's not going to limit us at all. We don't even have to think about the 32. So we know that our last significant figure should be in the ones place. So that little dot there, right after our 0, reminds us that this 70, right, has a total of 2 significant figures, or significant figures all the way out to the ones place, right? We need that information when we do the next step, right? When we're going to do that multiplying, right? And when we multiply, what's important is number of significant figures, right? So remember, the 5 and the 9 are exact numbers. That means they have an infinite number of significant figures. They have 0 uncertainty, right? They're not maybe a little bit more or a little bit less. They are right on 5 and 9 by definition, right? So what's going to limit that multiplication result is our 2 significant figures from that subtraction result. So when we put that in our calculators, I think we get 38.888888 on into infinity, if I am right. Is that right? Is that what everybody's getting? We get 38.888. Yep. All right. So again, to report it correctly, right, we should only write it down to 2 significant figures. Okay. So I'm going to round that to 2 significant figures, and I'm going to get 39 degrees Celsius. Now remember, my calculator is still sitting over here with 38.88888 in it. And I'm going to keep that there because I know I'm going to do something else with this value, right? I know I'm going to then convert my Celsius temperature into Kelvin, right? So I'm not going to clear my calculator just yet. I'm going to leave that in there, right? And sort of move along to the next part of this problem. So I reported my answer correctly to 2 significant figures for this first part of the problem, but I'm leaving in my calculator that value of 38.8888888 to use in this next step. Okay, so I wrote 39. I didn't write 38.888 because that would be too much. But my calculator is holding all those digits. So that is the value that I'm using to get this next result. Okay, but I wrote 39 to remind myself where the last significant figure should be, right? The last significant figure in my degrees Celsius result really should only have 2 significant figures. So it should end in the ones place, right? That 9 really is the last significant figure. So when I add, I'm going to be limited by the ones place, right? This has infinite significant figures. It has nothing to do with any significant figure results. It's not going to limit me in any way. Don't even have to look at that. Okay? So my result is going to have to end in the ones place. So when I add those two together, right, 38.8888888 plus 273.15, okay, I'm going to get a value, but I have to make sure that I round it to the ones place, right? So that's why I wrote it down here as 39 to kind of remind myself where that should be. You could have written it down as 38.8888, but underline that first 8 to remind yourself. That's the other way to do it. Should all get 312. All right. Okay. Questions on that? Sort of applying those rules in the order we do them, tracking the progress from one kind of math to the other kind. Okay. All right. So because we're sort of still, okay, Pauline, did you have a question? I'm sorry.
Yeah, could you explain how you got the significant figures for 5/9 times 70.
Oh, yeah. So 5 and 9 are exact numbers. So they have infinite significant figures. And 70 with that decimal point only has two significant figures. So the smallest number of significant figures is 2, definitely smaller than infinity. So our result of that can only have two significant figures. Yeah, I mean, it looks like the 5 and the 9 have one significant figure, but they don't, right? They come from a definition, right? So knowing where your equations are coming from is important. And our temperature conversions, all of the numbers in our temperature conversions are exact numbers. So they're not going to limit us in any way.
Thank you.
All righty. Awesome. Let me show you one thing that, Zara, I'm sorry. Did you have a question too?
Yeah, I did. I just wanted to ask, where does the 273.15 come from? If you could just explain that one more time.
So that actually comes, just roll myself back there. That is a definition of what the conversion between the Kelvin temperature scale is and the Celsius temperature scale is. So that is a by definition sort of thing. That's why it has an infinite number of significant figures. We have declared it to be true.
Okay, thank you so much.
Of course. All right. So again, because we're in the virtual world, I am not going to subject you to breakout rooms again. We have all survived that time. But what I will let you know is here are some problems you can practice with, and they were color coded so we could just do them in our different groups. But you can practice these on your own if you want a little more practice. You can kind of do them in groups by color. Each color has an adding and subtracting problem, a multiplying and dividing problem, and then a combination problem. So you can, well, obviously they're in the slides, but if you go into chapter 1 in Chem 131 and go into chapter 1 under the significant figure section, there will be 3 files that you can look at. One is this, it's the significant figure in class practice. Right underneath it should be the significant figure in class practice answer key. So you can just get the answers and check and see if you're right. If you're looking at this and go, oh my gosh, I don't, how did we even get that answer? You can go to the third file, which is the significant figure in class full solution guide. And it will walk you through just kind of like we did with our example problems for the multiplying and dividing and the combination. It's very long. It's about 8 pages long, and it'll sound just like me talking to you. It's almost like a transcript, but it will go through every one of those steps. What's the rule that we're using, right? Are we counting significant figures? Are we looking at position? What does my calculator say? How do I do the rounding? So you can really kind of sort of revisit all this again. And then if that's not enough, there's a couple of videos that I made that were referenced in the preparation guide that you can look at and decide if those are a little helpful as well. So it will be a sort of a consistent approach. So the same sort of approach that we did here in our class time. Okay. All right, let me make sure I didn't miss any questions back over here. So I think I've got everything. Okay, so let's take a little bit of a break here. Right, we'll take a little pause here. Things to jot down here before you wander off for a little break there is think about sort of your understanding of it. Which of those steps sort of along the way in the significant figures is the easiest for you, which is the most challenging? You know, what part do you feel like you have to slow down more? Do you want to investigate more in? That's what you can jot down there. So what we'll do is we'll put a little pause in our recording for a little bit, and we'll come back at 2:25. Work on units for a little bit, and then we'll finish up with our safety stuff. All right, so let's. Right, so we've got one more little topic, and then we'll move on to safety issues, and that is the topic of units of things. It's a short topic. All right, so here's your question. All right, we've got the chat box going again. All right, so person A is 145 tall and person B is 84 tall. Who is taller? Oh my gosh. I have fooled nobody, right? You've all picked D. All right, what information do we need to make that decision? Yeah, I probably shouldn't have told you we were going to work on units. I kind of spoiled it for you, didn't I? Yes, it is the units, right? We have no meaning, again, to just the numbers, do we? Right? We've got to know what units, what are the references for that? So without the units, the numbers have no meaning, right? I should make you say that out loud, right? This is going to be especially true, again, when you are actually taking those measurements, right? So when I ask you, well, what volume did you use? The answer shouldn't be just a number. It should be a number and a unit, right? So those units are going to be vital. They're the ones that give meaning, right? They tell us the size of things, right? What are those standards that we're using? Right. So every single measurement that we make or that another person makes has three components, actually technically four. But these are the three components. So think about these every time we're going to write down a measurement, right? Or every time we read about one, just on paper, right? There's going to be the number part, right? That's usually the part that we fixate on, right? It's going to have a unit, right? Got to tell me what we're measuring, right? Are we measuring volume? Is it a volume unit? Is it a mass unit? Right? What exactly are we measuring? And then it's going to have a precision. That's the significant figure part, right? How well does that piece of equipment work? Right? So by telling me your measurement to more or less decimal places or significant figures, that's telling me sort of about the kind of equipment that you use. Did you use something really fancy, right? That gave me a lot of precision, lots of significant figures, or did you use something that was right, not quite as well or as finely marked? The fourth component is the material. So what is it that you are measuring? Right? Are you measuring the volume of a solution? Are you measuring the volume of a block of wood? What is that material? So we will also be including the material eventually in our measurements as well. But the first three are absolutely required. Okay. And here's the beautiful thing. There are really only 7 units in the whole world, in the whole universe. We have 7 sort of fundamental properties of materials that we measure. And we're familiar with some of them, right? we're gonna use the ones with the little stars next to them. We're gonna start by focusing a lot on the top 3, mass, length, time. We'll eventually add in temperature. We did a little work on that today. And then number of things. That's going to be our chemical unit of the mole. We'll get to that in a couple weeks. You'll note that volume isn't here. Volume is really just length times width times height. It's the 3 dimensions. So it's sort of derived or follows from the length unit. So it is not really one of our basic units. It's a sort of a combination unit. All the other units, the hundreds and thousands of other units in the world, are all some combination of these. So everything will be defined in terms of these values, which is pretty cool. All right. Now, these units alone are not enough. Oh, there's a question in the chat box that says, are there other ways to count the number of things other than moles? Absolutely. You already know a bunch of them, right? Do you count by twos? Do you count by pairs of things? That's another unit, a pair for a number of things. Dozen, right? We do a lot with dozen, right? Pick up your eggs that way, or your cupcakes that way, or your donuts that way. Yeah, so yeah, there are other units that mean number of things. This is our official unit of counting things, and that's because we're usually counting very small things. Yes, awesome. All right. And again, we are measuring a lot of very small things, which means we have a lot of them, or we are measuring very big objects like the universe, or very small things like an atom. So the size of these units, right, we need to be able to modify them to account for, are we talking about a really big thing or a really small thing? And that is where our metric prefixes, our SI units, that's French for International System of Units. These prefixes are going to modify those units. All right. Now, depending on where you grew up, you may be more or less familiar with these, right? Again, here in the United States, we don't use the metric system, which is scandalous and terrible. But you might have grown up in a place where these were a little more common, right? The rest of us just kind of have to work our way around it. What's beautiful about these prefixes is they're all based on powers of 10. So they're all modifying that sort of fundamental unit by making it either bigger, those are the prefixes on the left, or making them smaller, which are the prefixes on the right. So we can have really big things and use our prefixes on the left, or we can measure very small things and use our prefixes on the right. Right? Which ones are we going to use? Well, we're going to use these ones here, the ones with the little stars. So this is your first list of things to memorize. These, what are they? 9 metric prefixes. You're going to be responsible for knowing without looking them up. Okay. And I think I might have sent you the list of things to memorize because we weren't in person for me to hand that to you. When we are together in person, it will be in your folder of goodies. This list of things to memorize. And this is the first thing on the list. Knowing these 9 prefixes for our metric system. All right, so we need to think about how they work, right? How does it work to know that pico is 10 to the minus 12? What does that mean? How is it modifying those units? All right, so here's how those units are designed to work. So the prefix unit is equal to the power of 10 times that base unit. So if we wrote mg, right, that's little m means milli, right? And G is our abbreviation for gram, right? So 1 milligram, right? So in red, I have the prefix part. And in place of that prefix, milli, I'm just going to put 10 to the minus 3. That's the meaning of milli. Milli means 10 to the minus 3, right? So 1 milligram equals 10 to the minus 3 grams, right? If I had a nanosecond, that's the N for nano prefix, and S the prefix for second, right? So again, in red is all the prefix part. So N, the prefix, means nanosecond. So 1 nanosecond equals 10 to the minus 9, right? That is what the meaning, right? If we go back at our chart, that is what the meaning of nano is, right? So that number means 10 to the minus 9 of whatever our base unit is. So you can see from our examples, the base unit can be a lot of different things. It doesn't always have to be grams. It could be seconds. It could be liters. It could be really pretty much any other unit we want, right? If we had this capital M, right, not to be confused with a little m, right? It's got a different meaning, right? Here's where I get to remind you to stop typing your work because autocorrect will capitalize everything for you. And the big M means mega. That's really different from milli. Milli is small. It means 10 to the minus 3. Mega is huge. It means 10 to the positive 6. Right? That's a million. right? There's a very big difference between a little m as a prefix and a big M as a prefix. So we need to be very careful with our writing, right? With our capitalization or not capitalization, right? So we can't write in all caps all the time because we have a lot of very specific symbols that mean different things, whether they're capital letters or small letters, right? So we need to be real careful about that. And we're going to write our leaders as a capital L, right? Because the little L looks like a stick or a 1 or an I. It's not clear. You'll find that chemists are very lazy. Well, we will do the minimum that we can get away with, but we're not going to sacrifice clarity for it. So we're going to make our L's as a capital L there. Right, that's part of thinking like a chemist. One of our goals for our class there. We'll be lazy, but clear. We're not going to sacrifice clarity for laziness. All righty. So 1 megaliter, right? Mega, that capital M prefix means a million. So 1 megaliter, a million, 10 to the 6th liters. Okay. And I'm going to encourage you to, when you're memorizing these 9 prefixes, to memorize them like a sentence, like a math sentence. 1 milli whatever equals 10 to the minus 3 of those whatever they are. Right? Let's kind of focus on not just knowing that milli is 10 to the minus 3, because that's not quite all the information you want. You want to get that number and that prefix in the right relative position. So thinking of it as a whole sort of math sentence, 1 prefix unit is equal to the number that we memorize times the base unit. That might help you to make sure that we're clear on that, especially if you're not as familiar with these prefixes, just from life experiences. Okay. Questions on this? Yeah, flashcards are helpful for memorizing, or a whiteboard or just a piece of paper, right? Just try and write them down, right? Without referring to that chart, and see how you do. There's probably a few that make more sense to you or that you're more familiar with, and a few of those odd ones probably towards the edges that you're less familiar with. Okay. All right. So here's what we're going to do with units. I love units. Units are going to really help us in our problem solving. But the first point, of course, they give meaning to our numbers. We saw that in the questions we've seen already. We are going to include our units in every single bit of data that we collect or work with, all of our calculations and all of our results, right? So the answer is almost never 7. It's 7 something. And more importantly, probably 7 somethings of a particular material. So yeah, your answer isn't really done until you've included the number, the right significant figures, the unit, and then the material of what we're talking about. We're going to have those as part of all of our results. They really and truly are a part of our measurements. We can't have a measurement that's just a number. So we are definitely not going to be ignoring our beautiful units. And then number 5 is the sad one, is that units are going to act like algebra. Okay, so we're going to have to talk a little bit about algebra here in a little bit. I'm just going to warn you, so I don't want anybody to be surprised by the next slide when we look at algebra. But ultimately, the units are going to be our friends. They are going to help us avoid having to do some algebra in the long run. So let's take a look at how they behave algebraically and how they're going to help us figure out how to arrange some of our relationships without having to do everything in a memorized or in an algebra equation solving kind of mode. We'll be able to sort of put our relationships together in a more mathematically simple way for us. All right. So from here on out, no skipping out on units, right? That's part of your portfolio as well, to include your units when appropriate in those problems or in those questions, because usually they don't have any meaning unless you've included those. All right, so brace yourselves. We're going to look at a little tiny wee bit of algebra coming up here. All right. Ah, okay. All right, so let's not get overwhelmed. Let's put our eyes in the very first box at the upper left. That looks like algebra. Yeah. So could you use all those little X's and Y's? Do you remember enough algebra to kind of group them together and simplify that, right? Can you put all the numbers together, all the X's together and all the Y's together and see if any of them cancel out or if they sort of increase each other, right? And make their powers go up. Um, give that a try. Take a little minute and try in that first little box to do a little bit of simplification and see if you can write that in a simpler form. So we're in this upper right box. Excuse me, upper left box. All right. How are we doing? A little thumbs up if you've gotten that kind of worked out a little bit. Okay. So again, the key here is that if our variables are in the top and the bottom, they can cancel out, maybe fully or partially. Or if we are, again, multiplying our variables together, their powers are going to add together. That was one of our early math practices. All right, so if we group all of our numbers together, the 3 and the 4 in the numerator and the 2 in the bottom, we get 6, right? If we look at all of our x's, we have x squared multiplying an x to the third. So again, those powers are going to add together. So we get x to the fifth. We have a single y in the top and a y to the third in the bottom. So one of the y's is going to cancel and we'll end up with y squared in the bottom. All right, so hopefully that algebra, like I said, to knock a little more rust off of that. But our units are going to work the same way. So if we look at the bottom right underneath that, right, it's very similar, right? Except instead of X and Y, I just put some units, kilograms and centimeters. And shockingly enough, right, it's going to give us a similar kind of result, right? So if we have kilograms squared times kilograms to the third, we're going to end up with kilograms to the fifth. So our units are going to behave just like our algebra variables, right? Same with our centimeters, right? We'll have a centimeter in the numerator, and we've got centimeters to the third power in the denominator in the bottom. Okay? So 1 centimeter from the top cancels one of the centimeters in the bottom, and we end up with centimeters squared in the bottom. All right. So we're going to have some math or some relationships where we've got all sorts of different units, right? So we want to be able to think of them as algebra variables so that they either cancel or combine, depending on what we're doing, accordingly. All right, let's put our eyes in the upper right now with all those variables, x, y's, and z's. We'll make it real challenging. We'll put 3 variables in there. All right, can you give that one a try and try and simplify that? So your job is to kind of group all the x's together, group all the y's together, group all the z's together, all the numbers on one side. Oh, right. So again, those variables are only going to cancel, right, if they're across from each other, one on the top, one on the bottom, and they may cancel fully or they may cancel only partially. Right? So for example, our y variable is going to cancel fully. There's a single y on the top and a single y on the bottom. Those are going to cancel. We're going to have no y's left over at the end of the day. So there'll be no y's in our final expression. When we put all our numbers together, I think we end up with a 10. And for our x's, we've got an x cubed in the top and a single x in the bottom. So one of our x's will cancel and we'll have only two x's, or x squared, up on the top there. And similarly for our z, there's only going to be a partial cancellation there. Okay. But our units, which are in the box right below it, are again set up very similarly. Right? I've used meters instead of X, I've used milliliters instead of Y, and seconds instead of Z. Right? But it's going to have the same exact form. It's going to end up the same way, right? We're going to group all our numbers together, and then our units are going to cancel just like X and Y variables, right? They really are a part of that measurement, right? So again, because that measurement has no meaning without them. So just like that 25Y stays together, our 25 milliliters is kind of a thing. So the milliliters part can cancel, and the 25 can get combined with all the other numbers as well. And we're going to end up with the same form over here. We're going to have 10 meters squared per second. All right. That is our big deal with our units, that they're going to combine algebraically. We're not going to do a whole lot more with that today, right? But we're going to see that when we start talking about dimensional analysis. So we just want to make sure that you are aware, right, of all these units. We're aware of all of those different metric prefixes, the ones that you're responsible for memorizing. And what we're going to do on Friday, again, whether we're here or in person, is work more on dimensional analysis, which means we're really going to be putting together everything we've done so far. So as much as you can do to kind of stay on track and start peeking ahead at that portfolio that's due, that just kind of spreads out the thinking and the work, and it lets your brain digest and master some skills before we build on them again. All right, a couple of quick questions and then we'll deal with our safety here. All right, so which of these is larger? So we're going to compare in the first row, 1 centimeter and 1 meter. Which is larger? Yep. Yep. So 1 meter is about 3 feet long. And 1 centimeter is about that big, just a little bit, about the size of a dice in a game. Yeah. Okay, how about the next row? 1 gram or 1 kilogram? What's bigger? A gram or a kilogram? Okay. Oh, we have some disagreements here. All right. So a kilogram, right? Kilo, the prefix means 1,000, 10 to the third. So 1 kilogram is 10 to the third grams. It is actually bigger than a gram. 1 kilogram is 1,000 grams. So it is actually 1,000 times bigger than a gram. All right. So yeah, so we had some disagreement on that one. So yeah, the kilo prefix is the only prefix with a small letter that's actually means a bigger unit. So if you were confused by the lowercase versus the uppercase, all the other prefixes have a capital letter for the ones that mean something bigger. All right, nanosecond and second, which is bigger? Yes, a second. A nanosecond is just a billionth of a second. So it's faster than a blink. Good. All right. How about this one? I'm gonna give you a tricky one. Which is the smallest unit of mass? All right, and for those of you who did not grow up here, that BL is an LB and it stands for pound. I have no idea why. Okay. All right. So smallest unit is in fact E. That is what our nano is a smaller prefix, but if you look real carefully at choice D, nano seconds. Second is not a unit of mass at all. So micro, that funny little U looking thing there, means micro, and it is smaller than milli, right? So the milligram. Actually, you might not even be able to type microgram on your chat box there. You don't have the Greek alphabet there. So yeah, so E is our smallest one. All right, and how about this last one? What is our unit when we do this calculation? 43 inches plus 6.1 inches plus 0.55 inches. What is going to be our unit? All right, great. Awesome. Yep. So again, just like algebra units, right? If we had 43x plus 61x plus 0.55x, we would have some number of x's. So yeah, so when we add things, they have to be in the same units for us to be able to add them together. If we were multiplying, then our result would be either A or C would be the right answer if we were multiplying. Okay. Oh my. Well, we're going to save that excitement for Friday. Then we'll learn about dimensional analysis on Friday. What we have still to do is to work on our little safety things. What I'm going to ask you to do is, because I have to verify that you have all been safety trained, I'm going to ask you all to type your name into the chat box so that I know we're all here and we're alive and we're paying attention. And then I might ask you to do it again sometime in the middle just to make sure we're all still here. Because again, you have to verify and I have to verify once we're in lab again, that we've all been through this safety training. So I will have to catch up with my friends who aren't here so we can make sure of that. All right. So I am going to stop sharing this screen and pull up our safety information while you're typing your names in there. Alrighty. All right. So again, you should be seeing sort of our opening slide that kind of looks like our beginning slide for all the chapters. That's how you always know that you're in the right class. All of our chapters have the same sort of branding on them. We are not going to do all of these things today. We are only going to do the first two and not even all of the first two. We're going to talk about safety. We're going to save the orientation for when we're in the lab and I can show you where everything is. But we will talk about lab report expectations. All of those other things, getting our lab partners, signing the safety agreement, our physical and chemical changes, all of our developmental practice 3, which is kind of our developmental activity for lab. That is all going to happen next week, next Thursday. We have decided, the chemistry department has decided to move all the labs forward a week, and we're going to take one out later on that we won't be doing So we will, I think I've got Blackboard all set up to account for all those changes in dates. And I believe I've already uploaded the new calendar that has all the labs shifted by a week. So this is, like I said, we're just going to do the safety part today. But again, if you haven't already done that, please type your name in the chat box. And that way I can verify that we were all here and we all did this. Okay. Awesome. Well, okay. So again, if we were in lab, this would be so much more fun. I would have you come and draw on the board and dress our nice little people. But can you think of some things that definitely should stay outside of the lab? Can you type those real quick into the chat box? We'll see how many we come up with. And I can guarantee you there's going to be some that you miss. We'll get to them all. All right. All right. How about things that should be in the lab? What should we be wearing, bringing, doing? So, all right. Pants. Thank you. Everybody always forgets pants. They love to dress our little people, but forget to put pants on them. All right. Awesome. Good. Yeah, you guys did a good job on the pre-lab of identifying what was wrong with our pre-lab person there. All right. Great. All right. So what I'm gonna do is we're gonna look at some things and we're gonna see there might be some things that we didn't think about, right? That didn't sort of come up here in your thing, in your answers in the chat box. All right. So inside the lab, we sort of have those non-negotiable things, which are the goggles. So those are going to be safety goggles. So those are not safety glasses, right? So if you've done a biolab and that was okay in biolab, that's not true, right? And I don't have my goggles with me because they are trapped in my office. But what we are looking at is we are looking at those goggles with the full splash protection all the way around. Those are the goggles that put dents on your faces. Those are the ones we mean, right? So those are the ones that you are expected to have. You can leave them in the lab. You can leave them in the drawers in our lab, or you can bring them back and forth every week. That's up to you. But they do need to be the full coverage ones. And we will be using them next week. So for our first lab activities and orientations. So make sure you've got them when we reconvene in person. Okay. In lab, you're going to want to bring your calculator, right? Because we're going to sometimes need to do some calculations before, right, we've actually finished collecting all of our data. You're going to need the lab manual printed out, right? So we don't want to be bringing in our tablets, right, and recording our data on that. We're going to want the old school paper. So and again, once we're back on campus, you can print more or less for free in the Science Learning Center. And then something obviously to write. Okay. All right, so I think we got a lot of the things to leave outside lab pretty well. Right? So food and drink, that was kind of first on everyone's list, obviously. I mean, that's true even in biology lab. I am hopeful that our classroom is empty during our lab time. So if it is empty, what we can do is we can actually leave all of our stuff in our classroom and not have to try and shove all of our personal belongings into the little cubbies that are in our lab. I'm almost 100% sure there's no class in there. And if that is the case, then we can leave everything that we're not bringing to lab in there and we'll lock that door so it'll be safe for us. But if not, then we'll have to put everything in the little cubby holes there. So try and travel light if that's the case. All right. So what else are we not bringing into class? So phone, I think a few people had already mentioned this. Yeah, we definitely want to leave our phones elsewhere. We don't want you to damage them, right? That's for starters. Secondly, is a safety issue, right? We don't want to be distracted by them. Um, let your friends and family know that for that 2.5 hours that we're in lab, you might not be responding to text right away. Because we're going to be focused on collecting our data and learning something cool, right? Seeing some fun things. So our cell phones aren't really a part of that. They're not our calculators, so we really don't need them in there. All that can happen is that they get destroyed. So we don't want that to happen. So we'll leave our little cell phones elsewhere. Watches and jewelry, I don't think anybody mentioned that. But I'm going to throw them in the same pile with um, scarves and neckties and really anything that's sort of dangly, right? Anything that's hanging down, right? So like hoodie ties, right? Long hoodie ties. Anything that is apt to sort of end up sort of being dragged through your chemistry experiment. So anything that hangs down like a long necklace, super long earrings, scarves, neckties, those sorts of things, right? We want to tuck those away, or maybe just leave the necktie at home for another day. But watches, bracelets, we want to be especially careful because they are usually sometimes pretty tight on your skins. When you wash, sometimes things can get behind or underneath them. And then you don't really notice, you don't really think about it until maybe you get home and 3 hours later, you're all itchy and scratchy under there because something got trapped under there and irritated you. So yeah, especially those little iWatch things, those little Apple Watches. That's just asking for them to get destroyed. So let's leave any of those kind of devices again in the little cubbies or back in our classrooms, um, so that you can be careful with that. Um, I will tell you, I do leave my wedding ring on, mostly because my husband insists on it. But I am very careful when I wash though. I'm always aware that that's a place where something could get trapped. So if you're not removing some particular object like that, like a ring or a bracelet for whatever reason, make sure that when you are doing the washing, that you're real careful to wash underneath it and dry underneath it. So that you don't have that chance of something being trapped underneath it that you're not aware of till later. I'm going to remind you too to make sure that you interrupt and ask lots of questions during this time. This is our time. This is our time for that. Okay. So if you're not sure about anything, now is the time to ask. You can ask later too, but now is a great time while we're all together thinking about it. All right. Oh. Right. Makeup. This does not mean what you think it means. Oh, great question. Are cardigans okay? Like a sweater? Yeah. They're actually probably, I'm gonna say it depends. Depends on if it's like one of those big, huge, flowy cardigans that's like all over the place. That's probably asking for trouble. But if it's like a smaller, tighter fitting cardigan, that's fine. Our lab can be cold. I think we have the cold lab, not the hot lab. So yeah, you're probably gonna want to wear maybe a sweatshirt or something, or a sweater to do that. Do we need a lab coat? The answer is that's entirely up to you. We don't provide lab coats, but if you want to bring one, you can leave it in the drawer or bring it back and forth. That's up to you if you want to wear a lab coat, but it is not required. All right, good, awesome. All right, so the makeup does not mean that you cannot wear makeup. Even though I can assure you, even though I haven't seen you, I assure you, you're all just beautiful. You don't need it, but if you want to wear makeup, And by makeup, I mean really anything you're putting on your body. So it includes all the classic makeups, mascara, blush, lipstick, all of that. But it also includes like lotion, right? It's dry out. We're using a lot of hand lotion and things like that. Or chapstick, lip balm. Those things we don't want to, you can wear them. Absolutely, you can wear them. But don't put them on in lab, right? Because in lab, there could be fumes and things that those materials, like lotion, might absorb those fumes, right? And then now you're smearing it all over yourself, right? Or your lip balm, right? That you're using your finger that may have touched who knows what. So if during the middle of lab you feel the urge to touch up your makeup or put lotion on, just make sure that you excuse yourself, right? Let me know that you're leaving. You don't need permission, but I do like to know where you've gone so I don't worry that you've fallen and you can't get up. Just let me know that you're stepping out and then you can go take care of that and then come right back in. So that's what I mean by makeup. Don't put it on in the lab, right? Do all that before we go in there. Okay. All right. Oh my gosh. Non-enrolled students. See, this is something that nobody thought about. Yes, please don't bring friends. All right. They haven't been trained, right? They haven't prepared. They're not ready for class. Our class is full. I don't know if you've noticed, we have 24 students. By the time we get all of our big grown-up selves into that lab, we fill all the seats in the lab. It is full. We don't have room for anyone else. That's why our enrollment is capped where it is. It's for safety reasons. So please don't bring friends. Tell them they can go wait outside in the Science Learning Center or have a snack in the vending room. But yeah, please don't bring friends. That's one that everybody forgot to include. All right, so in the lab, I think you guys got all these pants, specifically long pants. It's very cold out. That's not an issue now. As it gets to be warmer, right? Think about it, right? If you want to wear shorts to class, that's great. But bring like a pair of sweats that you can just kind of pull on. Again, our lab is the cold lab, so you might want them anyways. All right, closed-toed shoes. We've talked about gloves. I don't remember seeing gloves. Maybe I did see gloves. You're not required to wear gloves, but we do provide them, right? In all sizes, from extra small to extra big. So you are free to use gloves in whatever lab you want. They're always available to you. So make sure that you take advantage of that if you would like to. Historically, most students do, just out of an extra layer of precaution. Long hair tied back, right? That goes for everybody. So kind of along the lines of, do I need a lab coat? Is, well, if I'm not going to wear a lab coat, what should I be wearing? Right? So you want to wear something that's comfortable but not fancy, right? If you've got somewhere to go afterwards, don't dress for that event. Bring those other clothes and change into them. So you want to be wearing something that if something should happen and you should spill on it and maybe it ruins the color or puts a hole in your clothing, so you want to wear something that wouldn't be the end of the world if it got a little spot or a stain on it. And you should be comfortable. You should be able to move, but again, it shouldn't be so loose and baggy that every time you reach for something, you're going to be dragging a sleeve or something through your experiment or knocking over your graduated cylinder, right? So comfortable, but not fancy, right? Lab coat, again, optional. I hope I don't have to tell you this, but no smoking. You shouldn't be smoking anyways. It's not good for you, but definitely not in the lab, right? If you need a smoke break, make sure that happens before in your own car because we're a smoke-free campus. So, or work on quitting. So that's just good for you. We love you. We want to keep you. All right, but we do have some flames. We do have some labs where we will have open flames. So we do want to be careful and cautious about that. All right, when we're in the lab, walking and not running is super important. And not just any kind of walking, right? You need to be walking in the direction your eyes are facing, right? Which sounds obvious, but What happens is you're going to be at the hood, and you're going to be collecting your materials, and you're going to turn around real quick to go back and get going on your lab, and there's going to be someone waiting right behind you to get whatever's in the hood. So make sure that before you start moving in a direction, right, you have already turned your head, you have determined there's a clear path, and then you start walking, right? No sudden motions is what I'm saying, right? Maybe when you turn to go in a different direction, you kind of have a 2 count, right? So turn, look, 1,001, 1,002, and then proceed. Because again, there's going to be 24 of us in that lab. So that's when most of our accidents happen. It's usually that turning around and changing direction, where the person either waiting behind you wasn't paying as much attention, or you just turn real quick, or both. And that's how things get bumped and things get dropped and things get spilled at that point. It will happen. That's not the end of the world. But if we can avoid it just by sort of thinking about how we're moving our bodies around in that space, that would be great. So we'll do our best to try and keep the aisles as clear as possible. That might mean moving some of the chairs out of the way, especially for those inner rows, where it gets to be a little bit crowded. So again, you'll get a little more sense of that, how full it is when we're in the lab for real, next week, fingers crossed. All right. Okay. And we are wafting. We are not snorting. For some of our labs, the smell is an intensive property, right? It depends on what that material is. So that smell is a way to identify what that material is. So we have a lab where we will be doing that. So wafting, anybody know what that is? Have we heard that before? Yeah, good. All right. So what it is not, it's not taking that sample and sticking your nose in it and taking a good big snort of it. That is not what it is, right? So wafting it sounds very fancy and it looks very fancy. So if your sample is right here, you're going to wave those vapors towards your sniffer, towards your little nose there, right? And you're going to take little sniffs. So it's going to be very delicate, right? Like you're the queen, right? So waving, little sniffs, none of that. That's not going to work, right? That's not what we want to have happen. All right. So wafting and not sniffing. So we do have, like I said, one lab down about week 6, I think, where that's going to be an important test that we do. And nobody said this, but preparation. Preparation is going to be our number one sort of safety or accident avoider. It's going to help eliminate a lot of problems just by being prepared, sort of knowing what we're doing, the order we're doing it in, right? Right. Better yet, if you can get on board with your lab partner and kind of figure it out, how it's all going to work out ahead of time, that's great. But you should not be reading the lab manual for the first time the day of the lab, right? That should happen the night before at the very latest, right? So in your pre-labs for this, I had quite a few folks tell me that they weren't going to read the pre-lab until after they got the lab. I'm like, oh no, that is not going to work, right? So we definitely want the very first thing that you want to do in getting ready for lab is read the lab manual, at least once, preferably twice or thrice would be better. Because like I said, if you haven't read the lab and don't kind of know what comes next, you're trying to read and understand at the same time you're doing, and that's a recipe for disaster. It's also a recipe for taking really long in lab and not finishing on time. So we don't want that for sure. All right. Questions on what goes in the lab and what goes out of the lab? Okay. So let's talk about not just the do's and the don'ts, but like how are we going to make lab go better? Right? So there's things we can do that are going to make our lab results better, more educational, more fun. and more safe and more likely to give us good results. Okay, so there it is again, preparation. I will assure you it is not nagging until I say it the third time. And this is only twice. All right, so be prepared. That's the best practice, right? Being ready for lab, having fully read and digested the lab. We're going to talk about the lab before you get started. So bring your questions. We'll try and point out the sticky parts, but definitely answer any questions that anyone brings. So if you don't bring any questions, that's telling me we might not have read the lab manual enough. Okay, label everything. A lot of our experiments are done in water, right? We have a lot of water-based solutions where things are dissolved in water and the reactions happen sort of in that solution environment. Pretty much everything looks like a clear liquid, right? It all looks like water. It's a whole bunch of clear liquids. They all look the same. A lot of them don't have any smells, so we can't tell them apart just by looking at them. So if you haven't labeled it, then you can't really be 100% sure that what's in there is what you think is in there. So you might be mixing not what you think you're mixing. You might be mixing things that just give you no result. That's kind of the that's kind of the best case scenario, is that you mix the wrong things together and nothing happens. But you could mix the wrong things together, right, and have unforeseen sort of consequences there. So we don't want that to happen. So we have label tape available, multiple colors. You can color code to your heart's content, but make sure that you're labeling things so that you can tell one clear liquid from another clear liquid, because depending on what's dissolved in them, they're going to behave very differently. So it happens every semester. If somebody doesn't label something, or if their label comes off or something, and they mix these two things together that are actually two of the same things, and they get no result, and they wonder why they can't make sense out of their data. Then they get to go and start over again just to make sure that they know what things are. So it's a time saver. I mean, it takes a little bit of time at first, but it saves time in the long run. Okay. We should know where the safety equipment is. Of course, we're going to show you that when we get to lab. Placement of equipment, though, is important. That we can talk about now. So if you have a great big tall piece of glassware, this will be my big tall piece of glassware today. Where are we going to place this? Are we going to put it on the end of the table? In the middle of the table? Right between us and where we need to reach? On top of our lab manual? Right? We want to put it in a place that's safe, right? We want to be able to maybe take a measurement with it, right? So it needs to be flat on the table, but it doesn't need to be on the edge of the table, right? That's asking for trouble. And we definitely don't want to put it where we have to reach over a flame to get it, or reach around something else in order to get it, or right, set it on our lab manual. Your lab manual is probably going to get splashed. No matter how careful we are. I always get lab manuals, lab reports turned in that are all wet and covered with weird stains. That happens, but we'll try not to soak our lab manual by putting it in harm's way. So kind of always just be mindful of where you've placed your work, where you're collecting your data relative to where you and your neighbors are working. So several lab partners are going to be sharing a lab, one long lab bench. So, use the space you have, but don't infringe on other people's space. And just realize that you have to not just be careful of where your things are, but where the folks around you, where they have placed their objects as well. Okay. Which leads right into information sharing. All right. And we should be doing this. This is what science is, right? We talk to each other, right? We share information. We let folks know, hey, watch out for that step. The reaction happens really quickly. You need to be ready for the next thing to happen right away. Or watch for that. It's going to be really cool. You're really going to like that. Our lab should be loud in that sense, right? We should be communicating with each other, right? We're not going to be doing everyone's lab report for them, all right, and telling them how to write or answer those questions, but we are going to be communicating, right? That's the whole point of lab. Our lab should be a busy, happy kind of loud. It's not going to be an out of control loud. It's not going to be a crazy loud. But it should definitely not be dead silent. That means we're not doing it right if we're not communicating with each other, letting people know, hey, I'm right behind you. Please don't turn around too fast, or watch out, I've spilled something here, so don't step right in it. There should be a lot of communication happening. We should not be putting our unused solution back in a bottle, right? So you might take a little too much and feel like you're going to put it back in there. Why would we not do that? That seems like it's just, make sure that we don't waste anything. Why would we not put an unused solution back in the bottle? What do you think?
Could it be because of cross-contamination?
Could be cross-contamination, right? Right. A lot of things are based on what the concentration is. So by the time you've poured it in your container, you might have changed or altered its concentration a little bit, right? You also might put it back in the wrong bottle. Right? Then you might have ruined the whole bottle of everything for everybody. So yeah, so it's the same reason you don't like if you take too much milk, right? And you only drink a little bit of it, you don't put it back in there, right? You don't want to ruin the whole bottle of milk for everybody else. So yeah, so we want to be mindful. So being prepared lets you know, well, hey, I really only need about 30 mils of this. I don't really need a huge bucket of it. I just need a little bit of amount of it. So you can, again, we want to, use what we need to use for our experiment, but we don't want to be wasteful. We don't want to create a lot of extra waste. So be careful not to take more than you need. You can always go back and get more. Disposal, right? We want to know how and when to dispose of things. It's often in the lab manual. But sometimes, or almost always, I will remind you again before lab starts exactly where to dispose of certain things. Some of our waste all gets poured together. Some has to be separated. So again, just kind of watch out for that. And if you're not sure, ask. That is my job during lab. That is all I do in lab is answer questions. I get a full body workout during lab. I don't sit down. I will be swirling around that lab like a Tasmanian devil, just running around, answering as many questions as I can. I sleep really well on Thursday nights. So asking me all those questions, even if you feel like, oh my gosh, I've asked that already, that's fine. I'd rather you ask than not ask and end up putting that waste in the wrong place. So make sure that you take full advantage of my being there in lab with you. All right. And cleaning up, we talked about that a little bit, right? So washing after when it's time for you to leave the lab, making sure that you get under and in between all the little places, under the fingernails too, especially if you have long nails, make sure you check under there, make sure you get them all rinsed out very thoroughly. Any place where things might get trapped, like under rings or bracelets or watches, make sure that you're checking all those things. And I will tell you that if you need to leave lab, like in the middle, right, you need to go get something or drink or put on your lotion or whatever, you should wash your hands before you leave. Why? Why should you do that if you're going to just come right back in lab? Oh, okay. It's a stumper of a question there. All right. Well, suppose you need to go to the restroom, right? You're probably going to be maybe touching some very sensitive areas of your body. So you might not want to touch them with hands that have been in the chemistry lab, right? Might want to make sure that you have thoroughly washed your hands before you go to the restroom, so that if there's anything on your hands, right, you're not going to be, again, spreading whatever you might have been working with into very delicate parts of your body, right? So yes, the old saying is that chemists are really one of the few people that wash their hands before they go to the bathroom, um, and also after, obviously, as well. So again, if you need to use the restroom in the middle of lab, that's fine. Make sure that your lab partner is watching whatever you've got going on, right? You don't want to leave your experiment completely unattended. But let them know, let me know, go out and wash your hands, go out and do what you need to do, and then come on back in and we'll get back to work. All righty. Awesome. Okay, questions on those best practices? All right, so now we have even though we've prepared and we've labeled and we're careful and we're walking around, stuff still happens, right? There may be spills. If they're small, you can probably handle them on your own, right? If they're bigger or if they're on you, right, as opposed to just on the lab bench, then you're going to want to get me for the bigger spills. Little spills on yourself, you're going to take yourself right over to the water and start rinsing, and then get me. If it's a bigger spill all over you, then we have our fun showers. Let's hope we don't need to use them, but I will show you where those are when we're in person again. If you spill on the floor, though, make sure that somebody, it may be you or your lab partner or somebody, kind of monitors it until we can get that cleaned up. Because again, we don't want folks walking through it and then slipping and having a bigger accident than just a few drops on the floor. So yeah, so don't leave a spill in order to go get a paper towel. Monitor the spill and have someone else bring a paper towel. Right, so that's spills. Cuts and falls happens on rare occasions, but again, we have a first aid kit in the room. I have had the training. If it's something bigger than a simple little oopsie, then we will call for professional help at that point. So we will again take care of minor things, but if it's any bigger than what we can handle with a little first aid kit, we're gonna call for our professionals to come and help us out there. All right. All right. What if there's a fire? Oh my gosh. What should we do? We've said we're going to be working with flames. Right. So this picture is misleading. You are not a firefighter. You should not be picking up the fire extinguisher and attempting to put out the fire. You should be gathering yourself and leaving. So if there's a fire, your job is to leave. My job is to make sure you leave. My job isn't even to fight that fire. If you are on fire, we do have a fire blanket, and obviously the stop, drop, and roll is our first line of defense on that. But if there is just a general little fire in the lab, then we will evacuate. That's going to be our strategy, is evacuate. We're not fighting that fire. All righty. All right. And illness. Well, what happens if you're either sick the day of lab or you get sick during lab? What do you think you should do? Yes. It's always the first step. Let me know. We can figure things out. What you don't want to do though is suck it up and just show up looking terrible and feeling awful. Because I think the pandemic has taught us one thing, is that nobody wants your germs. Nobody wants to catch whatever you have. So yes, if you're not feeling well and you know it ahead of time, right? Let me know early in the day. We'll make a plan. We'll let your lab partner know. We'll figure out what to do. If you know you're going to be missing a lab in the future, right? Because you have a commitment or some appointment that you can't get out of, let me know. Maybe we can get you into a lab earlier in the week. There are no labs later in the week, so we can't kind of catch up after the fact. But what if you eat a sketchy little gas station burrito you know, at 11 o'clock and now it's 1:30 and you're in the middle of lab and you start to feel tragic and green and nauseous. What do you think you're going to do then? You can let me know, but I'm probably already going to know. I'm probably going to take one look at you and see how green you are and go, you need to leave. Yeah, there's yeah, you're not going to get any extra bonus points for trying to tough it out and then hurling all over our lab. No, that's not going to work. So yeah, so if you're not feeling well in lab, right, that is also an okay thing to let me know, and we'll figure out how to make that work for you and your lab partner. So yeah, there's no bonus points for being a martyr, right? For hanging out when you're feeling awful. You're not going to learn what we want you to learn from that lab. And you're probably not going to feel great, and it might just be making things worse. So yeah, so let's be kind to ourselves and to our whole class by handling illness in a sort of a responsible way. Alrighty. Okay. Are there any questions sort of on that sort of lab safety-ish part there? So then real quick, we're going to go through what we expect in a lab report and sort of the timing of things, because this was one of the issues in the pre-lab. This is one of the things that folks got not quite right. In addition to like not reading the lab manual first, one of the biggest problems was, when do we do our lab quiz? And the answer is not last. A lot of people thought it was after we turned in our lab report, and that's not true. It's not going to happen in class either. It's going to happen the night before. So after you turn in your pre-lab, that's going to unlock the lab quiz for the week. So we didn't have a lab quiz this week. So that there was nothing to unlock when you turned in your pre-lab. Next week, there is no pre-lab, but there is a lab quiz, right? To make sure that we still have all it'll be on safety issues. So it is actually already unlocked. You can take the lab quiz for next week as soon as we get out of here. I think it's set to open at 4 o'clock today. But in general, you're going to finish your pre-lab. That's going to open up the lab quiz. You won't be able to see it until you turn in your pre-lab. And then you'll be able to take that lab quiz. It's, like I said, it's about 10 minutes. It's a real quick one. Half of it is going to be on the week before, and half of it's going to be on the week that we're heading towards. Obviously, except for the next one. The next one's going to be all about lab safety. All right. Every lab report's going to have data. Every lab report's going to have some calculations or some questions about it. And most of them are going to have a pre-lab. So here's what's going on in the pre-lab. You really usually can't do the pre-lab until you've read the lab manual. It's going to kind of give you some guides there. So you should read the lab manual kind of like almost like a skimming, just to kind of get the sense of sort of what we're doing. But then you should read it more carefully, right? And really kind of like try and imagine yourself doing it and kind of making little marks there like, oh, I'm not really sure what that means, or that procedure doesn't make sense to me. I can't really imagine what that looks like. Those are the questions to bring to class, right? Those are the things that we'll talk about in a few minutes before we actually start the experiment. And if you don't leave your goggles in the classroom, make sure you've got them all sort of packed and ready to go that night before. Make sure your lab manual's printed out and ready to go. And then you can work on your pre-lab and turn it in, and that will open up the lab quiz, which will then be, like I said, about 10 minutes is what it's timed. So 10 minutes, and then it turns itself off, covers the previous lab and the current lab, right? So you don't really have time to just take the quiz without reading anything. You don't have time to look for those answers in just 10 minutes. So make sure that you have done some preparation before you take that lab quiz. All right, questions on those two things? So these are the two components that are going to happen on Wednesday night before lab. And these are the two things that need to happen so that you can attend lab. So if these two aren't done, that's telling me that we're not prepared. And again, because that's such a big component of safety, that's gonna be an issue, and we're gonna ask you not to be in lab that day. We don't want to do that. You don't want to miss lab. They're all super fun. Okay. Like I said, every lab has us collect some data or some observations if we're not taking a measurement with a number. Um, but every measurement's going to have a number, the right number of sig figs in a unit. Every piece of data that you collect, every lab report, I should say, has points available just for taking your data correctly, right? So you want to be able to take your data correctly. And our next 2 weeks of lab are going to have us practice that. We're going to work on some developmental activities next week and orient ourselves to the lab. And then our first real experiment is going to be in week 3, our measurement lab. Where it's all about how to take a good measurement. So we've got our first 3 weeks of the semester to learn how to take a good measurement, so that we aren't making those same mistakes over and over again as the semester goes on. All right. Then there'll be a place on your lab report where it will ask you questions, and then usually there's a space right there for you to show all your work, how you did that calculation, or a space for you to write your explanation. Sometimes you can set those up ahead of time. That might make things faster. Sometimes you need a separate piece of paper if you write really big, right? You might want a separate piece of paper to show all your work, right? Sort of thoroughly and in an organized fashion. Because that's a lot of what the lab report is about. Again, it's about communicating what you're doing, right? Showing how you went from the data to this result. It's not about getting the result. It's about showing how you got from the beginning to the end. So that is a big component. That's usually where the bulk of the points are. And then there's a post lab on most labs. Sometimes they're not related directly to your results, so you can answer them ahead of time. Most of the time, though, they have something to do with what you've measured, so you can't get too far ahead there. And then lastly, there is a lab exam that covers all the labs from the whole semester. That's way down in week 12, and we will talk about it when it gets closer. But I want to say right now, listen to the frog there. The frog has a good idea. The best way to prepare for that lab exam is to be prepared for every lab and be as fully present as you can for every lab. Save your lab reports, review them more or less right away, right? While it's fresh in your mind what you did. Because there really is no substitute for having been in the lab and having experienced that in order to be successful on that lab exam. In your purple folder, when we ever get together and I can give it to you, there's a chart that you can fill in as you go along, right? From week to week, sort of helping you to summarize what went on in each experiment, right? Again, in real time, so that you don't have to try and recall that all later. So you can add to it every week. That's also a little bit helpful, I think, to sort of, again, sort of capture what we did in each lab, so that when we get to that time for that exam, you're ready for it. Okay, I think that, yep, that is it. Any other questions on our lab report? Okay, again, you think of anything later, you'll let me know. So we did in fact use all of our time. I know it always takes longer when we're in this environment to kind of have me check all the places to check if you have questions. So I apologize that we did not get to end early. I was hoping we would. I'm going to go ahead and end our